let's move on to our torus. What the hell is a torus? Well, we should start here really, because what we're going to find out is just like we've covered what the circle, we covered the semicircle, we covered the sphere, the square, the triangle. We covered the tesseract the other day, which I'll go over one more time today because there were some issues there. And then we get to the torus that we're going to be doing today. What is all that about? Well, it's a geometric figure, allegedly. Okay, but it turns out that this thing called the torus is not really a geometric figure, just like all the others. It's a bunch of itineraries. It's a bunch of locations, and those locations, those itineraries, are swung around. So in order to understand, because people think that a torus, what you point to, that's a torus, a donut. No, that's not what a torus is. Not in geometry, not in the religion of mathematics. Okay? In the religion of mathematics, in the religion of geometry, trigonometry, and all that nonsense, okay, a torus is an itinerary that is swung around. Okay, so you can't point to an itinerary that is swung around. You can't even point to an itinerary. Okay, you're just pointing to a film of whatever is a bunch of locations. That's all you're doing. And so a bunch of locations does not a geometric figure make. Okay, so let's start at square one again. Unfortunately, I have to start at square one to look at the torus, just like I did with the others. And where do we start? Well, we start at the point and the line. Okay, and so here is the definitions. We work out of objectively from the definition. I didn't invent this stuff. Okay, this is what mathematical physics proposes. Okay, geometry, etc., trigonometry. A point is a primitive notion. Primitive means undefined. It's an undefined notion that models an exact location. That's what a point is. It's a location. A point is a zero-dimensional mathematical object. No, there is no such thing as a mathematical object. A point is a zero-dimensional, really non-dimensional what? Location. It's a location. There is no physical entity called a point. Now, there is a physical entity called a dot. Okay? You can point to a dot. And if it's three-dimensional, you call it a ball, for example. Right? It could be a cube, but generally people think of something round. Okay, fine. It's either a circle or a ball. That's what a point is. A line is a straight one-dimensional figure. No, there is no such thing as a one-dimensional figure. They're talking about itineraries. They're talking about locations. We have zero-dimensional locations. No, non-dimensional locations. One right after another. Building, constructing what is known as a line. And what is a line? It's an itinerary. It's a trajectory. Could be an orbit if it's circular. Okay? Having no thickness. No such monster having no thickness, meaning just one-dimensional again. And extending infinitely. No figure known to man can even be imagined to extend infinitely. There is no table that is infinite. Maybe God's table, I don't know. But no table you can imagine, no chair you can imagine, no tree you can imagine, no rock that you can imagine, no dog that you can imagine extends infinitely, okay? Meaning incessantly, because it's still growing, it's still extending. Okay, in either direction, for that matter. The notion of a line is usually left undefined. Yeah, they undefined it. I'll tell you why. Because they cannot reconcile the object known as line with the concept, dynamic concept known as itinerary. You can't blend line with itinerary. But that's what they do. They pictorially represent the itinerary with a line. That's where the cheating comes in. That's cheating. That's misleading you. Because people say, okay, I know what a line is. It's that stick. No, a line is not a stick, not according to mathematics. Mathematics says it's an itinerary. And I'm going to enforce that, because that's how they define it. So don't tell me that it's a stick. There is no such thing as a stick in mathematics. They have no use for sticks. They have use for itineraries, measurement, unrolling of the measuring tape. That's what they're doing here. That's conceptually and also by definition. I mean, it's a straightforward definition. What part don't you understand about unrolling a measuring tape? Because that's what they're doing. A line may be interpreted as a geodesic. What is a geodesic? Well, supposedly the shortest distance between 2 points, not like in the old days, a straight line, but on a curve. Supposedly you can't cheat and take the shortcut going straight, from one point to the other. You got to go around, because supposedly if you do it like on a planet like the Earth, well, you can't go through the Earth, you go around the Earth, around its surface. And that's what a geodesic is. That's why the geodesic became famous. But then it's not the shortest distance between 2 points. What it is, it's the shortest curvilinear, really, itinerary between 2 points on a sphere. That's the correct way to state that, not to say that's the shortest distance between 2 points, and then leave it up to you to figure out what did he really mean by that. I mean, I can go right through the center of the Earth and make it shorter if I can just cut across the Earth. Okay, I can take any small portion, arc, on the Earth, and I'm sure I can go in a straight line from one point to the other faster than I can go through the curve. Okay? And I'm not going to prove that. It's just common sense. Okay, we don't need to prove that mathematically. Okay, so this is what a point and a line are. Okay, there you see it. The mathematicians think that it's a turtle. Okay, that's leaving all these locations, and they're going to call that, all the series of locations, they're going to call that a line. So a line is not a stick. I want to make that point clear. It's not a stick. What is a line? A bunch of locations. What is a bunch of locations? An itinerary of a turtle. Okay, it's turtles all the way. Okay. So let's keep in mind the context here. We're not talking about lines. We're not talking about walls. We're not talking about sticks. And we're not talking about rocks or little balls or whatever. No, we're talking about locations. We're talking about itineraries. That's what geometry deals with. This religion called geometry, which is an attempt to mix physics with math. Okay, and okay, so here we have what point and line are for the purposes of physics. And in physics, it's objective. There's no second guessing here. It's straightforward. It's what you see in front of you. Okay, so I'm not going to mislead you. I'm going to tell you, look, what do you see in front of you? Well, the 2D point is just a circle. It's a round one. I'm going to do it with round ones because that's what people usually have in mind. You put a chalk against the board, it leaves more or less a circular pattern, unless you got a square chalk, I guess. But that's what it is. It's a circle. That's all it is. And what is a 3D point? Well, a ball. How's that? Is that difficult? So that's what a point is. And we call it a dot. And if you're going to use the concept location, don't call it a point, because the point is misleading. Because we don't know if you're referring to the dot or to the location by using the word point. If you're going to use location, why don't you do something radical and call it location? How's that for radical thinking, radical theorizing, and assuming, hypothesizing? Just call it what it is. If you're going to talk about location, call it location. Don't tell me point, because point is misleading. What is a line? Well, it's a stick. That's what it is for the purposes of physics. We have two-dimensional sticks, and we have three-dimensional sticks. Okay? And that's what a line is, because that's what's objectively in front of our eyes. Okay? In the case of the stick, it's a projection onto two-dimensional background platform, right? I can bring a stick and show you what a line is. I'll say, this is a line. And I can hold it in my hands and show it to you. Okay? Three-dimensional stick. So we have a two-dimensional stick, which I can't show you. I can only draw it. I can illustrate it, which is typically what is understood by the word line. And we have the three-dimensional stick. That's what a line is for the purposes of physics. Okay? Let's make sure we understand that's what it is for physics. Okay? Okay, some people have problems with that. They say, well, we have no use for your 2D and 3D point or for the 2D and 3D line of physics in geometry, mathematics. Those are some of the issues people raise. Rejoinders, etc. Okay, and this is our answer. We don't care if you can use them in math or not. That's what we have objectively in front of us. Okay, so we don't care if you can use it in math. We say line, and we refer to that thing that I just showed you, a little stick. And you say point, and that's a circle. That's what it is, a small circle. You want a square? Fine, no problem. We have no problem with you replacing the circle with squares or triangles or cylinders or whatever you want to put in there. I don't care. As long as there's something there, and that's what we'll call it. We'll say that's a point. That's a dot. Okay, and you say, well, I want to use the word point. Well, not if you're going to say that what you mean by that is location, and the little spot only represents the notion, the concept of point, of location. It's like saying I'm going to replace love with a heart. Yeah, or the goodness in you with an angel. Well, that's cheating. Are you referring to goodness or to the angel? Are you referring to love or to heart? Are you referring to dot or location? Make up your mind. If you're going to do location, call it location. Don't use words such as point and then say, well, it's undefined. It's primitive. You're primitive. You're a Neanderthal if you do that, okay? What have we before us is a dot and a stick. That's what point and line are, okay? These are geometric figures, okay? The point and the dot that I showed. In fact, let me put it up there again. I think it was this. Let's see if I can get it up here. No, wrong one. Give me a second here. Here, point and line of physics. Let me put it over here. Okay, that's what I'm referring to. Okay, so what you see there objectively is a dot. Okay, you want to call it point, no problem, but that's what a point is. That's what we have objectively in front of us. And what is a line? Is a stick. That's what we have objectively in front of us. Okay, these are geometric figures. Okay, physics has no use for abstract figures. None of these figures have anything to do with physics. We don't use these. We don't use the word point. We don't use the word line in physics. Okay, that's what we have in front of us, but we have no use for this stuff. Okay, I want to make sure that that's understood as well. We don't use this. We use real objects. Okay. And physics is about explaining mechanisms, okay, what the mathematicians call philosophy or semantics or beliefs or whatever they call it, okay. Abstract geometric figures cannot be used to explain a single mechanism in physics. That's why we don't use any of these. We have no use for point because I cannot explain a single phenomenon of nature using the word point, this abstraction, which is just a circle, or the 2D line, which is just a stick, okay. Math points and lines can only be used to describe, okay, which is the itineraries and locations, which they call point and line, right? And so please keep your locations and itineraries out of science. You know, if they want to use this stuff, I have no problem. But don't bring them into science. Don't bring them into physics. We have no use for points and lines. And that's just the introduction. So let's go quickly through the stuff I went through the other day, but I have to go through this to get to the torus, okay? Here's our circle. What was a circle? Just an itinerary, bunch of dots. What are those dots? They represent locations. So I shouldn't even be putting the dots. We should simply think of that as a bunch of locations. It's an itinerary. In this case, specific case, it's an orbit. That's all a circle is according to mathematics, because that's how it's defined. How is it defined? The curve traced out by a point, location, that moves in a plane so that the distance from a given point is constant. It's a point, in other words, it's a location circling a location called a center. That's what a circle is according to the mathematicians. So we have no figure. It's an itinerary, it's an orbit. Okay, let's get that through. Because people didn't want to introduce the circle when they want to do stuff there. No, I'm not going to let you introduce the figure, because we have no figures in mathematics. They have no use for figures. Okay, and what's the next one? The circle? Okay, I'm sorry, the semicircle. Semicircle, what is it? Half a circle. That's all it is. So it's the same itinerary, but stopped halfway. So what are we talking about when we say semicircle? Are we talking about a figure, geometric figure? No, we're talking about an itinerary, half an itinerary of a circle. Okay, so a circle, you can say, is a full circular itinerary. The semicircle is half of that. Okay, that's what it is. That's how it's defined. And again, if it's defined, it's a concept. It cannot be an object. We don't define objects in physics. We point to them. Objects we point to because we can point to an image, and concepts we define. So if these people are defining what a circle is, what a semicircle is, they're turning that object into a concept. And again, it is a concept because they're talking about itinerary, so no problem there. Okay, and so what is a sphere? Well, they get the semicircle and they twirl it around, and they call that a sphere. There's a definition, so you can read that a little later on your own. And yeah, that's what a sphere is. So what is a sphere? Is it a ball? Is this a sphere? Absolutely not. This is not a sphere. Or this one better. This is not a sphere. Okay? Assuming it's perfectly smooth, perfectly solid, la la la, it doesn't matter. That's not what a sphere is for the purposes of mathematics, because mathematics has no use for objects, for this. Mathematics only talks about the itineraries around a sphere. They can get rid of the sphere and they say, I'm going to deal only with the itineraries, with the locations. Okay, so let's get that straight. I'm not going to let you weasel out of that one. Okay, people want to say, no, here's a sphere and this is what we do with it. No. There's no figure called a sphere in mathematics, in geometry, official geometry. Okay. So one fellow asks this question. He says, you forgot to mention what a sphere is for you. Well, I just said it, but he even says it. It's a ball. It's a solid figure. That's what a sphere is, okay? So this one's not solid, okay? You can see it's spongy. Assuming it's a perfectly smooth ball, perfectly smooth, ideally smooth, and that it's solid, completely solid, made of a single piece, okay? There's no space in between there. We're talking about God's ball sphere up there in heaven. You know, it's a perfect sphere, not made of parts, made of a single piece, perfectly smooth, That's the ideal sphere. That's the ideal ball, really. That's what it is. Okay, and so that's what a sphere is. That's the notion we have of sphere. Is it an object or a concept? No, it's an object. It's an object because it has shape. That's the only condition. It needs to be an object. So it's not a concept. It's not an abstraction like people say, because they never define these terms. They don't know what a concept is. They don't know what an abstraction is. We had to define these words. We said, look, an object is that which has shape. A sphere has shape. It's an object. Period. We're done. No more arguing. Okay. Another fellow says the following with regards to this topic. He says, Bill says, a circle is an object because it has shape. Yeah. When it comes to a sphere, it's a concept because there is no perfect sphere. Poor folks. Poor folks. No, it's got nothing to do with that. Does a sphere have shape? Yeah, it has shape, so a sphere is a physical object. Is it an ideal object? Yeah, it's an ideal. So you can only imagine it. And you can talk about it, but there is no real physical sphere out there in the universe. Maybe God's sphere up there in heaven, fine. But no, it's the mathematical one that is a concept. And it's a concept not because it's got imperfections. It's got nothing to do with imperfections. It's got to do with the fact that the sphere of mathematics is the twirling of an itinerary. So it's not the notion that people normally have of what a sphere is. The word sphere in the minds of everybody, if you ask anyone, what is a sphere? Everybody will show you a ball. They'll show you something similar to this. They'll say, well, that's a sphere. That's not what it is in mathematics. Okay? So we have to understand that we have a problem with the definition. The definition doesn't match what they're pointing to. They're pointing to a ball and they say that's a sphere, and then they use something else, which is itineraries. And it turns out that when they point, they don't even point to a ball. They point to a bunch of lines that form, some kind of circular pattern there. Okay, so here we have the square. That was the next geometry we talked about. And the cube. What is a square? Well, it's an itinerary. It's a perimeter. A bunch of locations around the fence. That's what it is. And so the square is what you see, that little dot tracing all around. That's what a square is for the purposes of mathematics, of geometry. Okay. And then what they do is they take those itineraries and they put 6 of these itineraries, these walls that they think they built, and they say, well, now we built a cube. And so what is a cube? Well, it's a bunch of dots, or maybe lines, and the lines are made of dots. And what are those dots? Those are locations. What are those lines? A bunch of itineraries. So a cube, the so-called cube, is not a geometric figure also. Okay, so let's start there, because we're going to be building our tesseract with this stuff, and all we're talking about is locations, and people get lost in thought. They think now they're talking about figures. At no point in time are we talking about figures. There are no figures in mathematics. They have no use for figures. They only have use for itineraries and locations, but to give you the misleading impression that they're talking about figures and physics, they put something there that is visual, and they say, well, that's the point. What do you mean the point? Well, yeah, what is the point? Well, the point is undefined, see, because it's this little dot that we use to represent a location. And what is the line? Well, it's this stick, one-dimensional stick, this figure that we put to represent itineraries, a bunch of locations. And then with this, they're going to construct their cube. Okay, so let's keep that in mind. Let's keep the context in mind. We can't depart from this, because what they describe does not match what they point to. In this case, they do, because they show a bunch of dots. Is that a cube? Or, I think I've got it here. Well, no, here they put it in motion. Okay, they put the cube in motion. Okay. And so what are they rotating there? Well, they're rotating locations. They're what they're doing is moving time around, time and motion around. Okay, and here's one guy who builds his cube. Okay, and he tells you how it's made. He thinks he's putting walls there, and again, he's not showing squares, because those are not squares. A square is a sheet. Those aren't sheets. Those are just lines that he put there. Okay, because obviously if it's got a frame and the inside is different than the frame, then those are not squares. But this guy thinks he's got squares there, first of all. Second, he's going to build. He's going to construct. Is that what science, what geometry is? A construction of how you constructed your statue? How you chiseled it? No, in science we point to a cube. We don't construct it. But that's what these people do. They construct it piece by piece, and they're constructing it wrong, because this fellow is trying to construct his cube with these window frames. A window frame is not a square. Okay, so this is not only not a cube, but its constituents are not squares. So let's get that straight up front. This is not a cube, and those are not squares. Okay, so he starts out on the wrong foot, and on top of that, he's constructing something we don't do in physics for objects. We point to a cube. We don't construct it piece by piece and say, hey, this is how I made it. I don't care how you made it. Well, what material did you use? I mean, okay. And so this fellow continues, and now it gets even weirder because he's going to make a projection of this. And not just, what he's going to be doing really here is really building a hologram. He's going to shine light on the cube, and he's going to look at the shadow on the wall. And you can see the shadow on the wall does not match the cube that he's shining light upon and that he's moving around in that case. You can see that the edges of the cube on the wall, the one that's on the screen, okay, you can see those edges. He calls them squares, but they're not squares. He's distorted them, and in fact, he says that they become distorted. Yeah, no kidding, because he's not talking about squares. And one thing this fellow never learned, I guess all geometers never learned this, is that when you have a circle, here's a circle, okay, and again, this is a 3D circle, okay, just so that people say, oh, but that's not a circle. Yeah, it is a circle. People understand. Here you have a circle, okay? If I move it like that, now I have an oval. I no longer have a circle. So you can't move, you can't tilt a circle or a square or anything here. Well, I do have, no, I don't have it. Oh, here it is. Oh, let's see if I can get this. Assume this is a square, okay? Let's just assume. It's not, it's a rectangle in that sense, right? It's more rectangular than squarish. But if I move this sideways, I don't have a square anymore, okay? That's known as a rectangle. So if I started with a square, assuming it's more or less like that, when I move it sideways, I no longer have a square. You can't tilt a square and continue calling it a square, which is what this fellow did here, okay? And again, let me show you this. I think it's this one. No, wrong one, sorry. Let me get this one. You know, that's not a square, a bunch of squares that's on the wall. In other words, we don't have 6 squares on the wall. But this is what this guy keeps calling them, and he does tell you that they're distorted. No kidding. And this is important because that's what they're going to do with the tesseract. And again, people with tiny minds, tiny brains, they don't pick up on this. For them, it's all the same. They say, oh, I understood. You didn't understand squat. Let me show you what these people have. Well, let me first go to this one. Here's what a square is and what a cube is for the purposes of physics. What you see in front is what you get. This is what you ordered. That's what you got in the mail. Okay. So a square, there you see it. 4 equal sides. Okay, that's it. And we don't build cubes with squares. We point to a cube. We don't chisel it little by little and say, come back in a year and I'll tell you what a cube is. No, we point to a cube and say that's a cube. And again, it's a 3-dimensional projection onto 2 dimensions because again, it's an ideal figure. It's perfectly smooth, made of a single piece, and the only guy who's got that is God, okay, up there in heaven. We don't have it here on earth. So that's what a cube and what a square are, okay? Objectively, that's what's in front of our eyes, okay? Important to understand all that. So let's move on to the tesseract because they're going to build it also piece by piece. They can't point to a tesseract because when they point to a tesseract, we have no idea what they're pointing to. And this is what they're pointing to. They're pointing to this, okay, when they make it stand still. And, well, if you ask anyone to describe it, they would say, well, that's 2 nested cubes. That's what it looks like. Except for the fact that they're united by those lines that connect their corners. And so what we have is a little cube in the center, and then we have an irregular figure, on the sides of it. And again, we're supposed to look at or think of this in 3 dimensions projected onto 2-dimensional platform, background, or whatever. Okay? But even in the best of cases, if that's a 3-dimensional, in fact, they built some of these. I've shown it the other day. They built some of them, and all the ones that you see out there are 3-dimensional. They have length, width, and height. There is no other dimension. It's 3-dimensional. This is not a 4-dimensional anything. Okay? But the folks in relativity, they're the ones who use this, and they say time is involved, which some people also have mental problems trying to understand that. Yes, time is the 4th dimension, folks. Sorry to wake you up on that, okay? So what do? Well, what they do is, well, first let me show you my version of this, okay? And here it is. That's what a tesseract is. It's built by a Euclid cube that is growing through time, okay? And they take the first and last frame of that film. They superimpose one upon the other. They make a collage, and then they start rotating that collage. And a lot of people had problems with that. They said, "Oh, Bill, what do you say? You didn't understand." Well, here's first how they rotate it. Okay. In other words, or what I'm saying that they're showing there, they show a cube that's growing. Okay. They show the first and last frames of that film. They superimpose them, and then they start rotating that film. That's essentially what they're doing. And yeah, people say, "Bill, you didn't understand. You don't understand what you're talking about." There's one guy. Let me put his comment up there. Okay. People get upset. You didn't understand the idea of a tesseract at all. I'm not arguing that it's an object necessarily, but time has nothing to do with 4D mathematical geometry. We just showed that it does. With 4, with 3, and with 2. With 1 even. You know, what is a line? Line is a bunch of locations. It's an itinerary. That's what a line is. And, you know, if you're going to make a second location and a third one, you're involving time. Sorry to break it to you. And if a line, which builds up all the other geometries above it, is an itinerary involving time, all geometries, 100% of the so-called figures of geometry are made with time. All of them. There's not one, but show me one that's not made of time. Okay? So yeah, these people have mental problems. They don't understand this stuff. And they'll insist because that's how they've been educated. They've been brainwashed. They've been hypnotized in high school and college to believe that they were staring at geometric figures. I'm trying to clarify to them that they're not staring at geometric figures because they're not defined as geometric figures. How do you make a person who's been brainwashed, like this fella here, to understand that? You got to break his head, you know, with my dough roller. That's what he needs. That's what he really needs. This person has, again, mental problems. I'm not arguing it's not an object, okay? He says, the time component of the movie of the rotating warping hypercube has as much to do with its shape as the time component of the movie of a cube rotating to show its 3D-ness. There are static depictions of the tesseract. Yeah, no kidding. They turn all that time, and you don't even know what you're staring at. That's your problem. You don't know what you're staring at. You think you're looking at a figure because, you know, I'm staring at a standalone figure. But that's not what they defined. That's not the tesseract, that's not the torus, that's not the cube. What they're doing is moving things around in front of your eyes, and they're showing you the last picture. They say that's a cube, and you say, oh, okay, I understand that. It's a cube. It's a geometric figure. It looks like a Rubik's cube, right? No, that's not what it is in geometry. It's a bunch of itineraries only at the edges where the lines, you know, that give it that frame. That's what it is. That's all the cube is. And the cube is what they're going to use to build, what, the tesseract? So guess what? Not only do you have motion and time, but it's a bunch of locations. That's all it is. And they're going to be twirling these locations around, this motion they're going to be moving around. They're going to be moving time around. So yes, you are wrong, buddy. Sorry. Okay, try to wake up. Okay, you're the guy who doesn't understand. There are static depictions of the tesseract, just as there are static depictions of the 3D cube. Yeah, because you didn't understand what you're staring at. The cube inside a cube of a tesseract is not time slices. It's a projection. What is a projection? What we just saw a minute ago, a hologram? Is that what it is? Is that what a projection is? A shadow on the wall? What is a projection? See, these people don't tell you in detail what you're staring at, what they understood. They're just saying, you're wrong, Bill. It's a projection. Well, you didn't tell me anything. Okay, so until you clarify what you mean by projection exactly, are you talking about light, playing with lights? Is that what a projection is? A shadow? You block something from light and you get a penumbra or an umbra or whatever? Is that what it is? Completely irrational, perhaps, but in a much different way than what you are debunking. Well, no, I'm debunking the right one. You just don't understand what you're staring at. Okay? Another fellow says something along those lines. It's important to address these individuals so they learn something, perhaps, maybe. Sorry, but there is no small cube or growing cube in a tesseract. And none of the cubes are expanding. Okay, so you said, Bill, you're wrong. Okay, what's right? Let's find out what he proposes instead. Every side in that diagram has the same length, and each individual cube cell has the same volume as the cube depicted in the center. That's only a description. So far, you haven't told me anything. You haven't told me what those lines that connect the corners are. Okay, that's what we're trying to figure out here. Okay, I'm saying it's time. You're saying it's not. Then what is it? Okay, why would your lecture you on things you clearly don't understand? Well, because I like to talk about stuff that I don't know anything about. Okay, another fellow says, I think I've got someone else. Yeah, Fellow says the following. Got to get my dough roller on these guys. Okay. You say we can't have more than 3 orthogonal number lines you call dimensions because we can't imagine them. That is religion, not science. We don't imagine and believe. We assume and explain. Okay? Well, he's right. We assume and explain. What is it that he missed? I mean, he got that right so far, but he missed something. Okay? And that's what I want to clarify here. What did he miss? I think it's this one. Let me get it up here. Okay, this is what he... No, wrong one. Sorry. Give me a second here. Got so many of these. 1 second. I'll be there. There it is. This is what he missed. Okay. Put it side by side. What he misses is the criteria for defining irrational, the word irrational. What do we mean by irrational? Remember, this is rational science, so we had to define the word rational and irrational that no one in the last 10,000 years defined. They didn't define the word rational because everybody thinks that rational is what he believes in, and he who doesn't believe like him is irrational. Well, that's a little bit too subjective, so we had to create some criteria for what rational and irrational mean. And these are the criteria for irrationality: treating concepts as objects, known as reification congruitization, using inconsistent definitions or undefined words. Theory is inconsistent with or doesn't follow from the assumptions, describing, especially mathematically, and claiming to have explained. And the last one, which applies to this fellow, mechanism. Assumption doesn't work or cannot be imagined. Okay, and so the issue here is you can make all the assumptions you want, but you have to imagine your assumption. If you're going to explain to an audience and the audience cannot follow what you're presenting, remember you have to present the objects in front of you. And if you cannot present a 4-dimensional object, you cannot present a 4th perpendicular direction to the 3 directions known to man, then we cannot follow your presentation because you don't have an assumption yet. Okay, so you have to use an assumption before you can explain. And if you cannot present your assumption, which is the case here, you don't have a case. It's just that simple. So you lost, buddy. Sorry. Okay? You lost right there because you cannot present your assumption. Your assumption is what's irrational. We cannot picture the object that you're trying to present. And you cannot present 3 lines and a 4th one in perspective and say, well, that's the 4th line in perspective. Now you got to present an object. Please present the object and show that that object has 4 perpendicular directions. You got that? That's what you got to do. So no, it's not a question of belief. It's a question of, is your assumption rational? And objectively, it's not. So it doesn't even belong to physics if you say that you got a 4-dimensional object. Please show us the object that points in 4 perpendicular or faces in 4 perpendicular directions, mutually perpendicular directions. Okay, let's get to the tesseract here. Let's see if we can educate some of these bozos who think they know what a tesseract is. Okay, here it is. This fellow, he has this ridiculous thing, which he calls the tesseract. What he does, he's going to build it step by step. He's going to expand it, shrink it. He's going to do everything he can with it. Okay, very nice, looks flashy. First of all, he doesn't have a cube. That's a cube is not a bunch of window frames. So he doesn't have a cube to begin with. Okay, and then he's going to open it up, and he just does this out of his magic wand because where does he get those cubes? Okay, they're not in there now. He just pulled a rabbit out of the box. He's playing Jack in the Box. He's just pulling out a clown out of a box. That's all he's doing. And he's pulling out like 8 different clowns, one this direction, one in the other direction. What is the movie, 1,000 Clowns? With Jason Robards. Yeah. Anyone can do that. It's called magic, mathemagics. Okay. And what he does also, he does a projection. Okay. Well, this is someone else, but same thing. Okay. And they do what is known as a projection. They're going to take that cube, and again, they're going to tear it apart, and they're going to just pull cubes out of nowhere. You know, they say, look, I pulled a cube here, another cube here. He could pull 20 cubes out of there if he wants to. I mean, how did he do this? And people say, well, yeah, I understand. I know what he's saying. Well, you can't know what he's saying because, first of all, he doesn't even start out with a cube. None of those are cubes. What you have there is itineraries. Itineraries for the line, for the square, for the cube. and for the hypercube. All of them are itineraries. None of them are figures. So this guy is just inventing stuff, putting it there. It's flashy, and people just gawk because they don't know what they're staring at. What is that? Jesus Christ cross? This is nonsense. This is pure nonsense. Poppycock. Has no place in science. Okay, you got to be a mental retard to believe in this garbage. I don't know how else to say it. Maybe with dough roller behind in the hand. Okay. So yeah, this is absolute nonsense, and only mentally retarded people believe and pray to the tesseract. Okay, and most of them are relativists. Okay, here's the hypersphere, just in case. Covered it the other day, so that we can move on to our torus. Okay, and what is a hypersphere? It's just a growing balloon. That's all it is. It's a balloon through time, and you can see that the balloon is small, and then it just gets bigger and bigger and bigger. That's all it is, both in the static mode and in the dynamic mode. Okay? That's what all these figures are. They involve time. They involve time because each point that constitutes their sphere, their lines, etc., their geodesics, each point is a location. That's all we're staring at. A bunch of locations which are they're fooling your eyes by representing them with dots. And you say, oh, I know what it is. That's a dot. No, it's not a dot. The dot is pictorially representing a location. None of those are geometric figures. Math has no use for figures. Geometry has no use for figures. None of those are figures. Figure belongs to physics only. Math has no use for figures. Okay, so here we go with the torus. Finally get to the torus. Okay. Hopefully people understood that all so-called geometric figures of geometry, of mathematical physics, relativity specifically, are just locations and itineraries. That's all they are, nothing more. Okay, no geometric figure. Okay, so we have this. We have a torus that is a bunch of locations, bunch of dots. What are those dots? What are they? They're locations. So we're staring at a bunch of locations which are represented with little dots, two-dimensional dots, which you're supposed to think of as zero-dimensional dots, whatever that means. Okay, that's what you're staring at. So you're not staring at a donut. You're staring at a bunch of locations, and the only reason you can see those locations is they represented each location with a dot. Do we understand or not? Okay, let's hope it sinks in some of the brains out there, pea brains, okay? So you're not staring at a donut. You're staring at locations that somehow, fool you into believing you're staring at a donut. Okay, so that's a mirage. Okay, so here's your torus, but this one is made a little differently. Okay, here it goes. Let's get it in there. Okay, this one's made with lines. Okay, geodesics they're called. Shortest distance between 2 points, again points, on a curved surface. Okay, okay, so we have two different kinds of toruses here. One is made of points, the other one is made of lines, but not really that different because remember the lines are made of points. So these two things are really identical. It's just that they give you the misleading impression in one case that it's made of points, the other one it's made of lines. But they're the same. They're all made of points. Okay? So what is a torus? Well, we got to look at the definition so that we understand where we're at. And here's the definition. Okay? This is the formal definition. Let me get myself back in here. Someone said to me, there is no flowing in or on a torus. It's a shape, a static object. Absolutely not. Learn what a torus is. For that, you got to look up the definition. This is from the Wikipedia, but you can find the same definition here everywhere. Okay, here it is. A torus, okay, is a surface of revolution. What is a surface of revolution? Have you ever heard of that term? Well, if you took college physics or at least perhaps even in high school physics, a surface of revolution has to do with calculus, okay, with integration, okay. For those who took that, they know what I'm talking about, okay, but forget about that. Just a notion. What do you think a surface of revolution means? Is it overthrowing a government? Is that what revolution means? No, revolution means you're going to rotate it. You're going to put it in motion. You're going to build something by scanning, by sweeping. Okay, that's what revolution means in this context. Generated by what? Revolving. You're going to revolve this thing around the circle. You're going to revolve it around somehow. You're going to sweep. Okay. Revolving what? A circle in three-dimensional space about an axis that is coplanar with a circle. So what is a torus? It's built with circles. And the circle, remember, they said it's just the outer portion, it's just the circumference. That's the circle, according to some of these bean brains who think a circle is just the little ring. No, right here they're saying a circle, they're treating it like this, like, a plane surface. completely continuous surface. That's how they're treating it here. And they're going to say that that circle, which they call disk, some people call it disk, is going to sweep around and construct, build, through time, through motion. They're going to build the famous torus. Okay? Do we understand each other or not? This is what a torus is. It's a surface of revolution which revolves. It's a circle that's moving around. What is a circle? A bunch of dots, a bunch of locations. And again, there's two notions. One is the circumference and one is the disk. Which one is the circle? Well, we don't know. We'll find out someday. Okay, because they deliberately have it ambiguous so that you don't really know which one is the circle. Is it the circumference or is it the disk? So why do we need the word circle? I mean, let's just talk about disk or circumference, right? Why do we need the word circle? And yeah, they put these words in there and people get confused and then they think they're staring at a geometric figure when they're just looking at a bunch of locations. They don't even realize this. Okay, and so what do they do next? Well, they do the weirdest thing you can imagine, and that's you had that torus, right, which was swept around by a circle, right? What they're going to do next is they're going to put this thing in motion. They're going to twirl it around. They say, oh, the twirling donut or a torus or whatever. So they have the motion of the locations. That's what's moving here. We have locations that are moving. All these locations are twirling around. They're orbiting. What are they orbiting? The center, which is another location. All we have so far is motion. We have no physical object in front of us. We have no geometric figure. All we have is motion, locations, lines. What are lines? Locations. What are circles? Locations. It's all location. It's all motion. It's all motion, time. There's not a single geometric figure in all of mathematical physics. Okay? Not even space-time, which we'll be dealing with. Okay? Okay, so now you know what a torus looks like and how ridiculous it is for these people to say, oh, we're going to twirl the torus. Okay? It is ridiculous because these people don't understand what they're doing. And they fool people through the images and people say, well, I understand what I'm staring at. No, you don't. It's a bunch of points. That's what you're staring at, locations. Okay, so here's the conclusions. Okay, math figures are not figures. Not a single figure in all of math because math has no use for figures. Okay, math phys only has itineraries, line, circle, etc. Bunch of locations. All math solids are hollow. There's not a single solid in all of mathematical physics, in all of so-called official geometry. Tesseract, not equal to 4D. It's not a four-dimensional anything. No such thing as a four-dimensional object, and relativity specifically states that the fourth dimension is time. So when these people say that the tesseract is a four-dimensional object but it does not involve time, it's people who are mentally retarded, people who have no understanding whatsoever of what they're listening and what they're seeing. They don't understand what they're seeing, what they're staring at. So they are mentally retarded, and this is what I offer as a solution for those people. Okay? Tesseract is two nested cubes. That's the static image. That's what you see there. You see one cube inside another. That's it. And the fact that they built these things, okay, in real life, I should have put this up there, but some people have built it with sticks and Legos and whatever. They built two nested cubes. And that's what a tesseract is, objectively, when you have a static image, just two nested cubes. What is a tesseract in real life? The notion these people want to convey to you is that it's an expanding cube. And that's a concept. That's not an object. That's not a figure. Okay? We're talking about at least two objects, the beginning and the ending object. That's known as two objects. Two objects is the definition of the word concept. Okay? Hypersphere, also not a 4D object, just a balloon that's expanding. That's all it is. What's a torus? Is it 4D? Because we have time, right? The torus is now spinning on itself. What are we talking about? Well, we're talking about time, right? Hopefully, we're talking about motion. You just saw it in motion. So is that a four-dimensional donut? Is that what you're going to tell me? I mean, when you see it static, you say, well, that's static. That's a three-dimensional donut. Fine. How about when it's twirling? Now we have motion. Now we have time. Has the donut turned into a four-dimensional object because now it's rotating on itself? It's got time. So again, a boy standing still, he's three-dimensional. But as soon as he moves, he turns into a four-dimensional boy because now time is involved. Now you have a clock to time him. This is the issue, okay? Torus, bunch of locations and itineraries. That's all the torus is. And when rotating square, cube, tesseract, whatever, etc., mathematicians are spinning motion. They are spinning time. They are spinning a web of nonsense, of poppycock.